amount of coating material that you required, inlet and outlet operating temperatures. So these are all the variables which you have to take into considerations for efficient and effective encapsulation by air suspension techniques. So this is the diagram. So in this, as you see, this is the coating chamber, and this yellow one particle, these are the solid core particles which you have to suspend in the upward airflow, and then you spray the coating material on it. So in this, by this air suspension technique, you encapsulate the drug, you encapsulate the core material. So this is also this figure also shows the air suspension technique. In air suspension technique, this is in the bottom, this is the air flow of the particles which are suspended in upward flow, and this is the nozzle and air distribution. This is the air distribution plate, and this is coating partitioning, coating spray. So by this method you can coat the core material. So the cyclic process is repeated perhaps several hundred times during processing, depending upon the purpose of microencapsulation, the coating thickness desired, until the core material particles are thoroughly encapsulated. So this air suspension technique, this process is repeated several hundred times until you ensure that the core material particles that are thoroughly encapsulated, when you ensure the coating thickness you desire that is correct, then you stop this process. So this is the cyclic process which is repeated several hundred times until the core material particles, they are thoroughly encapsulated. So the supporting air stream also serves to dry the product while it is being encapsulated. So as in this air suspension technique, by this technique you can encapsulate the drug. Also you have used this supporting air stream to dry the product. So drying rates, they are directly related to the volume temperature of the supporting air stream. So there is one disadvantage of this technique, air suspension technique, that is agglomeration of the particles to some larger size is normally achieved. So agglomeration of particles is achieved by this method. So this is the one disadvantage of this technique. So by this we complete with the first technique, that is the air suspension technique, which is also known as Wurster process. So second technique of microencapsulation is Coacervation phase separation. So coacervation phase separation, this is the process. It consists of 3 steps. In the first step, first of all, formation of 3 immiscible phases. Immiscible phases include solvent, core material and the coating material. So first of all, formation of 3 immiscible phases. Then second step is deposition of the coating material on the core material. Third step is rigidizing the coating, usually by thermal, cross-linking or desolvation techniques to form a microcapsule. So this method, coacervation phase separation method, this method, it consists of 3 steps. First step is formation of 3 miscible phases, then you coat the material on the core material, so deposition of the coating material on the core material, then you rigidize the coating by thermal technique or cross-linking technique or desolvation technique to form a microcapsule. So this is the picture, this is the diagram which shows the coacervation phase separation. So this is core material dispersion in solution of shell polymer. So this is the solution of shell polymer, core material, this is the core material dispersion. So this is phase separation. So you separate the coacervate from the solution. So by this, this figure shows the separation. You separate the coacervate from the solution, then coating of core material by micro droplets. This is the coating of material, core material by micro droplets, and this is finally coalescence of coacervate to form a continuous shell around core materials. So this is all about the coacervation phase separation. So this technique, coacervation phase separation technique, in this separation of coating material onto core material, that can be obtained by a few methods. One, you can separate the coating material onto core material by changing the temperature. addition of incompatible polymer, addition of salt, addition of non-solvent, polymer-polymer interaction. So these are the few methods by which you separate the three phases. So in this coacervation phase separation, we have few methods by which you can separate the coating material onto core material. So first method is temperature change method. In temperature change method, first of all, disperse 2% weight by weight ethyl cellulose in cyclohexane, then heat the mixture to boiling point to form homogeneous polymer solution, then add core material with stirring, then cool the mixture in room temperature with stirring, finally filter it and collect the microcapsules. So this is the temperature change method. So changes in temperature that causes the separation of coating material from the solvent, and this method is useful when the solubility of material depends upon the temperature. So in this we use the coating material is ethyl cellulose in cyclohexane, and the core material which you coat which you have to coat is core material is N-acetyl para-aminophenol. So this is in this method, temperature change method, core material is N-acetyl para-aminophenol and coating material is ethyl cellulose in cyclohexane. So second method under coacervation phase separation is incompatible polymer addition. So incompatible polymer addition, first of all dissolve ethyl cellulose in toluene to produce the 2% weight by weight volume solution, then disperse crystalline methylene blue with stirring, slowly add liquid polybutadiene, solidification by the addition of hexane, finally filtration and the drawing of microcapsules. So in this method, the polymer which is chemically not compatible, that has more affinity towards solvents, added to the coating solution. The polymer which is to be added should have no interaction with the core material, and it should be incompatible with the coating material. So in this incompatible polymer addition method, the core material is methylene blue hydrochloride and the coating material you use is liquid polybutadiene to the this ethyl cellulose in toluene. So this is the coating material and this is the core material. So third method under coacervation phase separation is salt addition method. So these are all the methods by which you coat the core material. So salt addition method, in salt addition method dissolve, first of all dissolve the core material in corn oil, then emulsify in 10% gelatin solution at 55 degrees Celsius, slowly add 20% sodium sulphate solution, then rigidization is done by 7% sodium sulphate solution at 19 degrees Celsius. So finally filtration, washing with water and spray drying is done. So salt addition method, in this method soluble inorganic salts can be added to aqueous solutions of certain polymers. The salt that is added should be soluble in water, should precipitate the polymer from the solution, should not have any interactions with the core material. So in this method we use the core material is this oil soluble vitamin in corn oil, and coating material is this 20% sodium sulphate solution which is added to the gelatin, 10% gelatin solution. So next method under this technique is non-solvent addition method. So in this method, first of all prepare the 5% solution of CAB in MEK. So what is CAB? CAB is this cellulose acetate butyrate and MEK is methyl ethyl ketone. So first of all you prepare the solution, 5% prepare the solution of CAB in MEK, then add the micronized methyl scopolamine with stirring, then it is heated to 55 degrees Celsius, slowly add isopropyl ether, then slowly cool to the room temperature. So in this technique phase separation can be induced by addition of non-solvent for given polymers. The non-solvent used should have more affinity towards solvent which is used, precipitate the coating polymer, should not have any affinity towards the core material. So in this technique we use the core material, that is methyl scopolamine hydrobromide, and coating material is addition of isopropyl ether to cap in MEK. MEK is methyl ethyl ketone. So, last method under this coacervation phase separation technique is polymer-polymer interaction, also known as complex coacervation. So, based on the ability of cationic and anionic water soluble polymers to interact in water to form a liquid, polymer rich phase complex coacervate. For example, gelatin below its isoelectric pH possess positive charge and gum arabic is negatively charged. So, in this material, in this technique, core material used is methyl salicylate and we get the microcapsules which is of 20 to 800 microns in size. So, this is the complex coacervation technique. In this technique, first of all, dissolve the core material in aqueous gelatin solution at a 40 to 50 degrees Celsius, then add gum arabic solution, then adjust the pH between 4 to 4.5, then cool to room temperature, then microcapsules with rubbery shells are formed, then it is cooled to 70 degrees Celsius, then treat with glutaraldehyde and finally you have to dry the microcapsules. So, this is all about complex coacervation technique. So, with this we complete with the second technique of microencapsulation, that is complex coacervation technique. So, this is the third technique, that is multi-orifice centrifugation. So, in this technique multi-orifice centrifugation, we use the centrifugal forces for encapsulating liquids and solids and the encapsulated product that can be supplied as slurry in the hardening media and in the form of a dry powder. So, in this technique we use the rotating cylinder with 3 circumferential grooves. So, intermediate groove, it has a orifice and we have the tubes to carry coating material to upper and lower groove. So, there is counter rotating disc which have cores production rates of 50 to 75 pounds per hour by this technique. So, these are the processing variables of multi-orifice centrifugation technique: rotational speed of the cylinder, flow rate of core and coating material, concentration and viscosity of coating material, viscosity and surface tension of core material. So, this is all about the multi-orifice centrifugation technique. So, next technique is pan coating method. So, this pan coating method, this is the oldest industrial procedures for forming small coated particles or tablets. In this pan coating method, the particles are tumbled in a pan or other device while the coating material is applied slowly. Solid particles greater than 600 microns in size, they are generally considered essential for effective coating, and the medicaments are usually coated onto various spherical substrates such as sugar seeds and then coated with protective layers of various polymers. So, this is the pan coating method and this figure shows the pan coating. So, this is the air atomizing nozzle by which you spray the this is the spray zone and this is the exhaust air. So, this is the pan coating method, but this method is not used nowadays. This is the oldest procedure for forming small coated particles or the tablets. So, next technique is spray drying and spray congealing technique. So, in spray drying, in modern spray dryers, the viscosity of solutions to be sprayed can be as high as 300 millipascals second. So, this spray drying and spray congealing technique, in this the core material is dispersed in a liquefied coating substance. In spray drying, core materials, they are dispersed in a polymer solution and then sprayed into a hot chamber. The shell material solidifies onto the core materials as the solvent evaporates, such that the microcapsules obtained, they are of polynuclear type or matrix type. As I told you earlier, microcapsules, they are of 3 types: polynuclear, mononuclear and matrix type. So, by this technique you get the polynuclear microcapsules or matrix microcapsules. So, spray drying, it is effected by rapid evaporation of a solvent in which coating material is dissolved. So, chitosan microcapsules cross-linked with 3 different cross-linking agents like TPP, tripolyphosphate, formaldehyde, glutaraldehyde. So, these are the chitosan microspheres which are prepared by spray drying technique. So, in the spray dryer, it includes air heater, atomizer, main spray chamber, blower or a fan, cyclone and product collector. So, this is the diagram which shows the microencapsulation by spray drying. So, then come to the spray congealing technique. By spray congealing, it can be accomplished with spray drying equipment when the protective coating is applied as a melt. So, core material is dispersed in a coating material melt rather than a coating solution, and coating solidification is accomplished by spraying the hot mixture into a cool air stream. So, waxes, fatty acids and alcohols, polymers which are solids at room temperature but meltable at reasonable temperatures, they are applicable to spray congealing technique. So, with this we complete with spray drying and spray congealing techniques. So, next microencapsulation technique is solvent evaporation technique. So, in solvent evaporation technique we have 3 steps. First of all, first step is formation of a solution of the drug into an organic polymer phase. So, this is the first step, you have to form the organic polymer phase. Second step is emulsification of polymer phase into an aqueous phase containing a suitable stabilizer, thus forming a OW, oil in water emulsion. So, first of all, formation of organic polymer phase, then you have to add the emulsifier, and this is the oil in water emulsion is formed. And third step is removal of organic solvent from dispersed phase by evaporation leading to polymer precipitation. So, in this step solvent evaporation is done and polymer precipitation is done, and finally these are the microspheres which you form. So, this is the formation of microcapsules by solvent evaporation technique. Next technique is electrostatic deposition. So, this method is suitable for both solid and liquid droplets. In this method, core and coating materials, they are imparted electric charges by means of high voltage. Core is charged and placed in the coating chamber. Coating material is charged in solution when it leaves the atomizer device prior to spray as a mist. So, since both are positively charged, coating material gets deposited on the core due to electrostatic attraction. So, next technique is vacuum deposition technique. This is not a popular technique. In this technique, the coating material is vaporized in chamber in which core material is present. Coating material gets deposited on the core particles, and the core particles, they are moved on conveyor system and then counter hot vapors of coating material which gets deposited on them. So, next technique is polymerization technique. So, in polymerization technique, monodisperse microgels that in the micron or submicron size range, then precipitation polymerization starts from a homogeneous monomer solution in which synthesized polymer is insoluble. Particle size of resulting microspheres depends upon the polymerization conditions including monomer composition, amount of initiator and total monomer concentration. So, in polymerization technique, we cover the 3 methods. One is interfacial polymer method, in situ polymerization, then matrix polymer. In interfacial polymerization, the 2 reactants in a polycondensation meet at an interface and they react rapidly. So, in this method, first of all dissolve the monomer in liquid core, then disperse in aqueous solution of dispersing agent in dropwise manner, add a multifunctional amine, then you get the microcapsules with the polymerized shell. In situ polymerization, in few microencapsulation processes, direct polymerization of single monomer is carried out on particle surface. So, for example, cellulose fibers, they are encapsulated in polyethylene while immersed in dry toluene. Usual deposition rates are about 0.5 micrometers per minute and coating thickness ranges from 0.2 to 75 microns. Next method under polymerization technique is matrix polymer method. So, in this method a core material is embedded in a polymeric matrix during formation of the particles. It prepares the microcapsules that contains the protein solutions by incorporating the protein in aqueous diamine phase. So, this is the extrusion. Next technique is extrusion technique. So, advantage of extrusion technique is that it completely surrounds the core material with the wall material, and this extrusion technique, it involves forcing a core material dispersed in a molten carbohydrate mass through a series of dyes into a bath of dehydrating liquid. So, when contact with the liquid is made, the carbohydrate case hardens to entrap the core material. Then the extruded filaments are separated from the liquid bath, dried using an anti-caking agent such as calcium tripolyphosphate. This process is particularly useful for heat labile substances such as flavors, vitamin C and colors. So this is the single emulsion technique. In single emulsion technique is, first of all you add the emulsifier to the core material, emulsification is done, then water in oil emulsion is done, this is the cross linking is done by chemical method, thermal or enzymatic method, then washing, and finally you isolate the microspheres. This is the single emulsion technique. This is the double emulsion technique. In this you do the emulsification double times. First of all you add the encapsulant, emulsification is done, then oil in water emulsion is done, and in oil in water emulsion you then again add the emulsifier, then oil in water in oil emulsion is done, then cross linking, washing, and isolated microcapsules are formed. So with this we complete with the microencapsulation technologies or various methods of microencapsulations. So next come to the physicochemical evaluation of microcapsules. So in physicochemical evaluation, so we can evaluate the microcapsules by the morphology of microspheres. The surface morphologies of microspheres, they are examined by a scanning electron microscope. Second method of evaluation is atomic force microscopy. So multi-mode atomic force microscope, it is used to study the surface morphology of the microspheres. Then particle size determination is done. In particle size determination, approximately 30 milligram particles is redispersed in 2 to 3 ml distilled water containing 0.1% tween 20 for 3 minutes using ultrasound, then transferred into the small volume recirculating unit operating at 60 ml per second, and finally microparticle size can be determined by laser diffractometry technique. Next evaluation technique is sieve analysis. So in this, separation of microspheres into various size fractions can be determined by using mechanical sieve shaker. In this sieve shaker, a series of 5 standard stainless steel sieves, they are arranged in the order of decreasing aperture size. Then 5 grams of drug loaded microspheres, they are placed on the uppermost sieve. Sieves are shaken for a period of about 10 minutes and then the particles on the screen are weighed. So next evaluation technique is polymer solubility in solvents. So in this, cloud point can be used for the determination of solubility of the polymer in different organic solvents. So next technique is viscosity of polymer solutions. So absolute viscosity, kinematic viscosity, intrinsic viscosity of polymer solutions in different solvents can be measured by a U-tube viscometer. In this, polymer solutions, they are allowed to stand for 24 hours prior to measurement to ensure complete polymer dissolution. So this is the density determination method. In this, the density of microspheres can be measured by using a multi-volume pycnometer. Accurately weighed sample in a cup is placed into a multi-volume pycnometer. Then helium is introduced at a constant pressure in the chamber and allowed to expand. This expansion results in a decrease in pressure within the chamber. So 2 consecutive readings of reduction in the pressure at different initial pressures are noted. From 2 pressure readings, the volume and the density of microspheres is determined. So next is bulk density. The microspheres fabricated are weighed and transferred to a 10 ml glass graduated cylinder. The cylinder is tapped until the microsphere bed volume is stabilized. The bulk density is estimated by the ratio of microsphere weight to the final volume of a tapped microsphere bed. So this is the angle of contact. Angle of contact is measured to determine wetting property of a microparticles, to determine the nature of microspheres in terms of hydrophilicity or hydrophobicity. So angle of contact, it is measured at a solid air water interface. Advancing and receding angle of contact, they are measured by placing a droplet in a circular cell mounted above objective of inverted microscope. So next, in vitro methods. In vitro methods, we have 2 other methods, beaker method and the dissolution apparatus method. So these are the 2 methods for in vitro studies. In beaker method, the dosage form is made to adhere at bottom of the beaker containing medium and stirred uniformly using overhead stirrer. And in dissolution apparatus method, dissolution medium used for study vary from 100 to 500 ml and speed of rotation vary from 550 to 100 rpm. So with this we complete with the physicochemical evaluation of microcapsules. Next come to the applications of microcapsules. So agricultural applications include, it reduces the insect populations by disrupting their mating process, protects the pheromone from oxidation and light during storage and release. Next is catalysis, safe handling, easy recovery, reuse and disposal at an acceptable economic cost. So metal species such as palladium acetate and osmium tetroxide have been encapsulated in polyurea microcapsules and used successfully as recoverable and reusable catalyst without significant leaching and loss of activity. So in the food industry also this technique is useful. Adding ingredients to food products to improve nutritional value can compromise their taste, color, texture and aroma. Sometimes they slowly degrade and lose their activity or become hazardous by oxidation reactions. So in most important are the pharmaceutical applications. So in pharmaceutical industry, lupin has already been launched in the market. World's first cephalexin and cefadroxil antibiotic tablets for the treatment of bacterial infections. Then Zorprin controlled release tablets are used for relieving arthritis. Quinidine gluconate controlled release tablets are used for treating and preventing abnormal heart rhythms. So these are also the few applications. By this technique you can prepare the prolonged release dosage forms, enteric coated dosage forms, mask the taste of the bitter drugs, reduce the gastric irritation. You can use to aid in the addition of oily medicines. So to protect the drugs from environmental hazards, the separations of incompatible substances is done by this technique. So microencapsulation can also be used to decrease the volatility. Hygroscopic properties of core materials may be reduced by this technique, and in the fabrication of multi-layered tablet formulations for controlled release of medicament contained in medial layers of tableted particles. So these are the summary of application of microencapsulation techniques. So finally, conclusion is that the microencapsulation technique offers a variety of opportunities such as protection and masking, reduced dissolution rate, facilitation of handling and spatial targeting of the active ingredient. So this approach facilitates accurate delivery of small quantities of potent drugs, reduced drug concentrations at sites other than the target organ or tissue, and protection of labile compounds before and after administration and prior to appearance at the site of action. So in future, by combining various other approaches, microencapsulation technique will find the vital place in novel drug delivery system. So in this chapter we will cover the topics which I summarize the topics. First of all, brief introduction, then advantages of microencapsulation, then disadvantages, then fundamental considerations, various methods used for encapsulation, reasons for encapsulation, physicochemical evaluation of microencapsulation. Last we have done the applications of microencapsulation. So this is all about this topic, that is microencapsulation. Thank you.